Physical Science 20, Heat, Lesson 1, Linear and Volumetric Expansion. This goes along with the H1 and H2 assignment. Important to know as we work through this unit is that change is always equal to final subtract initial. Therefore, the change in length will be the final length subtract what the initial length was. A change in volume will be the final volume subtract the initial volume. And change in temperature is also final temperature subtract what the initial temperature was. If you have a moment, bring up The Day After Tomorrow on Netflix or Crave or whatever you stream movies on and watch from 1 hour, 39 minutes, and 32 seconds in. And you will see something that looks like this. A cold air mass moving down, and as it moves down in New York City, it blows the windows out of the buildings. Now, why is this happening? Well, it could be, that phenomenon we see when we take a glass out of the dishwasher and add cold water to it, and it shatters. I don't know if you've ever done that. I've done that a time or two. Probably related to today's topic, but odds are it's probably happening because the glass and the frame around the glass have two different coefficients of linear expansion, which means that, undergoing a temperature change will cause any material to contract, but metals and glass don't contract at the same rate. Each material has a unique coefficient of linear expansion. This is because some materials expand or contract a lot when heated or cooled, such as iron or steel. Then there are other materials, such as glass, that are hardly affected by a change in temperature. The windows in our classroom are glass with an aluminum frame. And if that was rapidly cooled, that frame would contract quite quickly because metals conduct heat quite easily. And on top of that, it also shrinks a lot compared to glass when it's cooled. So that rapidly shrinking aluminum frame would put pressure on the glass and cause that glass to then blow out. Now I'm going to grab a copper rod and we're going to look inside that copper rod. So a copper rod is going to be made up of copper atoms. Of course, I've exaggerated the size of these atoms. They are much larger than the average copper atoms. And they are also standing still, which is weird because atoms don't stand still unless they're at 0 Kelvin. And there's no way it's that cold. So these guys should be vibrating, something like that. And that's what heat is. When things heat up, they just vibrate more. And when I add heat to this copper bar, it's going to cause those atoms to start to vibrate more violently, which causes them to then move away from one another. And that is why materials expand when heated. They're vibrating more, bounce off of one another more violently. It causes them to spread out. And that leads to linear expansion. So our change in length is equal to our alpha value multiplied by the initial length of the material multiplied by the change in temperature. Now, alpha is a coefficient of linear expansion that we find on the pink sheet under coefficients of thermal expansion. That's the alpha column. Example, an aluminum baseball bat has a length of 0.86 meters at a temperature of 25 degrees Celsius. When the temperature of the bat is raised, the bat expands by 0.00016 meters. Determine the final temperature of the bat. So I'm looking for final temperature. I'm told it's an aluminum bat, so I can get the alpha value off of my data table. We're told the length of the bat is 0.86, so that's my Li, and that our initial temperature is 25 degrees Celsius. When the temperature of the bat is raised, we're told it expands by 0.00016 meters. That's how much it expands by, that's how much its length changes by, so delta L is 0.00016 meters. Now if we're looking for TF, well, the only formula we've seen with TF is delta T equals TF subtract TI. I know Ti, but I don't know delta T. So before I can use this formula, I will have to find delta T. If I look at change in length is alpha Li delta T, well, I know delta L, I know the alpha value, I know Li, so that means I can solve for the fourth variable, which is delta T. So to get delta T by itself, I will divide both sides by alpha Li. That way, the alpha value of aluminum will factor out on the right-hand side, as well as Li, which means delta T is now all by itself. And it is equal to delta L divided by alpha Li. I can substitute my numbers in. I make sure I double bracket the denominator. And when I run it through the calculator, I get 8.08898 degrees Celsius with two significant figures because every number in my equation had two significant figures. Now, let's find that TF. So delta T equals TF subtract TI. I need to get TF by itself. So that means I have to move TI. So since TI is subtracting from TF, I will then add TI to both sides. So on the right-hand side, negative TI plus TI cancel each other out. Now TF is all by itself, and it's equal to delta T plus TI. Now to keep track of significant figures, when I'm adding, I like to stack them. So my change in temperature is 8.08898, and my initial temperature is 25 degrees Celsius. And that will give me 33.08898 degrees Celsius. 25 degrees Celsius is where I run out of significant figures right after the 5, so that's where I draw my round-off line, and I keep what's in front, which means the final temperature of the bat when it expands by 0.00016 meters, that means it is 33 degrees Celsius. We have seen how atoms in a long metal bar expand linearly, but logic tells us that this expansion must occur in all directions. This equation helps us determine the change in volume due to a temperature change. Delta V is our change in the material's volume. Vi is the volume of the material initially. Beta is the coefficient of volumetric expansion, which is found on our pink sheet right next to those alpha values. And of course, delta T is change in temperature. The radiator coolant reservoir on a car holds 4.80 liters when the engine is cold. If the reservoir was topped up on a day when the temperature was 12 degrees Celsius, and the reservoir has an operating temperature of 92 degrees Celsius, what is the volume of the radiator coolant? Well, they gave us a beta value. That's nice. I don't have to look it up on the data table. So, I am looking for, well, let's see what we've been given. I'm told that the car holds 4.80 liters. That's my VI. When the engine is cold. And that it was initially filled at 12 degrees Celsius, so that's my initial temperature. And when it's operating, it's going to warm up to 92 degrees Celsius, so that's my final temperature. And then what is the volume of the radiator coolant when the car is in operation? So I'm looking for the final volume. So, well, I've got initial temperature and final temperature, and I know delta T equals TF subtract TI. So TF, 92, subtract 12, which is my TI, gives me 80. Both run out after the 2, which means I have two significant figures, so my change in temperature is 80 decimal degrees Celsius. Now I can use delta V equals beta VI delta T. I am looking for, this time, delta V, because if I'm looking for VF in the end, I'm going to have to find delta V. So I substitute my values in, run it through my calculator. The degrees Celsius to the -1, which means it's in the denominator, will factor out with the degrees Celsius in the numerator, which leaves me with liters. So I wind up with 0.1582 liters. Change is always final subtract initial. I'm looking for VF, so to get VF by itself, I will add VI to both sides. So negative VI plus VI, those will cancel each other out, and VF will equal delta V plus VI. So delta V is 0.1582 liters. My initial volume is 4.80 liters. Both numbers run out of significant figures 2 spots after the decimal. So 4.95 then rounds up to 4.96 liters. And that brings us to the end of the lesson. Now remember, the whole entire reason we make a variable list is to try to determine what can I solve for if I can't get to what the question is asking me for. Like in the previous example, as soon as I saw TI and TF, I knew I could find delta T. I couldn't jump all the way automatically to VF, but by looking at my variable list, I can say, what have I been given? And with what I've been given, what other things can I find? So I can keep adding to the variable list until I get to my final answer. All right, good luck. H1, H2.